Hello everyone, it's my pleasure to share our recent work with you here, entitled Study Intelligent Metasurface Enable LEO Satellite Communications Relying on Statistical CSI. It has been published in IEEE various communications letters. Here's a brief outline. We will start with the background. Recently, as part of the goal to achieve global connectivity in 6G, LEO satellite communications have gained significant attention due to their extensive coverage. To achieve higher communication capacity, multi-beam satellite technology is widely used, relying on digital precoding to reduce interference among UTs. However, digital precoding poses challenges to the onboard processing capabilities of high-throughput satellites. Additionally, LEO satellite communication scenarios have two important characteristics. The one is that one satellite typically needs to serve a much larger number of UTs than the number of beams it can generate. And the other one is that the high mobility of LEO satellites made it difficult to obtain perfect instantaneous CSI. Recently, an advanced structure called Study Intelligent Metasurface has emerged, and for simple, I will refer to it as SIM. This structure consists of multiple layers of metasurfaces, each composed of multiple meta-atoms capable of controlling the phase shift of EM waves. When EM waves pass through these meta-atoms, they act as secondary sources, generating secondary waves, propagating to all meta-atoms in the next layer. The signal received at each meta-atom in the next layer is the weighted sum of the signals radiated by all meta-atoms in the previous layer. So we can perform linear operations on signals in the wave domain by controlling these meta-atoms. Motivated by this advanced SIM technology and the requirements of traditional digital precoding techniques on satellite onboard capabilities, in this letter, we designed a meso-satellite network based on SIM. As shown in Figure 1, SIM is placed in front of the antenna array, and the signal for each UT is directly transmitted from the corresponding antenna, and the beamforming process is entirely completed by SIM in the wave domain at the speed of light. Compared to traditional multi-beam satellites, this system avoids the digital precoding step and its associated processing energy and energy consumption, and reduces the number of required RF trains. Additionally, considering the characteristics of satellite communication, we also investigated two related issues. On the one hand, to reduce the pilot overhead for probing channels, we use statistical CSI instead of instantaneous CSI when designing algorithms. On the other hand, to further enhance the performance when serving a large number of UTs, we also designed a user grouping algorithm and an antenna selection algorithm. Next, I will introduce the signal module. As described by this formula, the signal travels from the transmitted antenna to SIM, then to the UT after passing through SIM. The propagation matrix of SIM is composed of interior propagation matrices and phase shift matrices corresponding to each layer. The elements of the interior propagation matrix can be obtained from the principles of really small field diffraction theory, so we can achieve beamforming by controlling these phase shifts. For the channel from the scene to UTs, we model it as a region channel. Moreover, due to the high altitude to the satellites, the arriving directions of multiple passes are almost the same. Thus, the non-loss part of the channel has the same correlation as the loss part. Next, I will introduce our specific algorithm flow. First, we perform user grouping. We fix the number of groups to the minimum value that can serve all users, because the channels in capacity optimal loss MIMO systems are orthogonal to each other. In this letter, as described by this expression, we aim to minimize the maximum value of all COC within each group. We use a greedy algorithm to quickly obtain a suboptimal solution. In general, first, calculate the COCs between all users. Then, separate the users with the largest COCs as initial groups, and then assign the remaining users to these groups one by one, ensuring that each assignment minimizes the maximum COCs within each group. Once the groups are determined, each user needs to be assigned an antenna to transmit their signal. It's worth mentioning that this aspect differs between the scene-based communication system and traditional digital systems. In traditional systems, each antenna transmits signals containing information for all users. However, in our system, each antenna transmits signal for only one user, meaning that we need to select a unique antenna for each user. Different selection schemes may result in varying performance. In this letter, like this expression, we aim to minimize the sum of interference power when power is evenly allocated. This power can be solved by the Hungarian algorithm when phase shifts are determined. We randomly select multiple phase shifts and use the Hungarian algorithm for each random phase shift setting, recording the sum of interference power, and finally selecting the antenna selection scheme corresponding to the minimal sum of interference power. Finally, we simultaneously optimize the phase shift of scene and the power allocation method to maximize the ergodic sound rate under total power constraint. Since the expression of the ergodic sound rate is difficult to obtain, we instead choose to optimize a tight upper bound on it. It can be seen that the expression of this upper bound only requires the statistical CSI, which includes the power attenuation coefficient and the loss component of the channel. We use the AO algorithm, employing both gradient descent and iterative word filling algorithm to alternately address the phase shift of scene and power allocation. These two algorithms both ensure that the objective function does not decrease at least, ensuring the convergence of the AO algorithm. Next, I will present the simulation results to show the effectiveness of the proposed algorithm. These are the main settings of the simulation. Specifically, for the selection of the region factor of the channel, we refer to the recommended value of 3GPP using suburban scenario unless otherwise specified. These two figures respectively show the sound rate and convergence behavior of the algorithm on the different numbers of wires. From figure A, we can see that the sound rate initially increases with the increase of the number of wires, then tend to stabilize. This is because there is a complex trade-off between increasing the number of wires and reducing the interwire spacing. The former improves the beamforming ability of scene, while the latter reduces the effective energy radiation from one metatom to next layer, thereby reducing the beamforming ability. Figure A also compares the cases of using three types of CSI-driven optimization. We can see that although the performance with statistical CSI is not as good as with instantaneous CSI, it is still better than with estimated CSI, especially in urban scenarios with larger region factors. Figure B verifies the convergence of the AO algorithm, and the larger the number of layers, the slower the convergence. These two figures compare the performance differences between using the proposed grouping method and rhythm method from two perspectives. You can see that the performance after using the proposed grouping method is better than rhythm one, and becomes more pronounced with increasing transmit power and total number of UTs. For the latter, this is because as the total number of UTs increases, the selection space for UT combination increases, resulting in smaller COC between UTs after grouping. In Figure A, we also introduced digital recording systems and hybrid recording systems for comparison. We can see that even without the need for a large number of RF trans and without the digital recording step, string-based multibeam technology can still achieve performance comparable to digital systems. In conclusion, we provide a brief summary of this work. Overall, we have designed a sync-enabled micro-satellite communication system which implements pre-coding in the wave domain, reducing energy consumption and latency compared to traditional systems using digital pre-coding. Additionally, for the case of real satellite communication systems, we have designed a user grouping algorithm and used slow-vary statistical CSI instead of instantaneous CSI. Simulations results demonstrate the effectiveness of the algorithms and show that the proposed system can achieve performance comparable to traditional digital systems. Here are the references used in this presentation. Thank you for your listening very much.